Hello friends, so far I have mainly discussed about metals. Although I have explained the origin of semiconductors and insulators, I have not discussed about them in detail. In this lecture, I am going to start our discussion on semiconductors and insulators. Before starting our discussion on semiconductors and insulators, let me summarize what we have done so far. We started with free and independent electron gas model. The model considers core electrons to remain attached to the nucleus, forming heavy immobile atomic cores, while valence electrons form an ocean of electrons moving around freely and taking part in electronic transport process in solids. Electron gas model ignores electron-ion and electron-electron Coulomb interaction. This is known as the free and independent electron gas model. We discuss both classical and quantum model. Although free and independent electron gas model can explain metals to some extent, there are some failures, most notable being the anomalous Hall coefficient in metals. Moreover, free and independent electron gas model fails to explain the existence of semiconductors and insulators. Then we included electron-ion interaction while solving the time-independent Schrödinger equation. The ions are arranged in a lattice and provide some periodic potential to electrons. Such electrons are known as block electrons. We treated block electrons using two different models, A, nearly free electron model, and B, tight binding model, and found satisfactory explanation for anomalous Hall coefficient in metals. We also got some idea about the origin of metals, semiconductors, and insulators. Now we are going to learn in detail about semiconductors and insulators. In terms of electrical conductivity, materials can be classified as metals, semiconductors, and insulators. At room temperature, metals have very high electrical conductivity. Semiconductors have medium electrical conductivity and insulators have very low electrical conductivity. Note that we are talking about electrical conductivity at room temperature, because at very low temperature, both semiconductor and insulator have very low conductivity. Conductivity differed by several orders of magnitude. Because carrier concentration also differed by several order of magnitude at room temperature. Not only the resistivity in metals and semiconductors differ by several orders of magnitude, temperature dependence of resistivity also have opposite trend. For example, resistivity of metals increase with increasing temperature, as shown in this plot. On the other hand, resistivity of semiconductors decrease with increasing temperature, as shown in this plot. This is a simple cartoon showing the origin of metals and insulators starting from isolated atoms. These are the atomic energy levels in an isolated atom. If you bring the isolated atoms close to each other, energy bands start to form. If the Fermi energy is here and the energy bands are not overlapping, we get an insulator, because the green band is completely full and the blue band is completely empty. On the other hand, if two bands are overlapping, then both the bands are partially occupied, leading to a metal. Let us now discuss about the electronic band structure of two of the most famous semiconductors, silicon and germanium. Both of them have diamond cubic crystal structure. A is the lattice parameter, R is the bond length, and Eg is the band gap. Note that at 0 Kelvin, all the states below Fermi energy are occupied and all the states above Fermi energy are vacant. Thus, at 0 Kelvin, semiconductors are insulators. Occupied levels are called valence band and vacant levels are called conduction band. At finite temperature, some electrons are excited from the valence to the conduction band. As a result, both valence and conduction band are partially occupied, such that electronic transport can take place. Note that electrons can be excited from valence to conduction band in case of silicon and germanium because they have a small band gap of 1.1 electron volt and 0.7 electron volt. Thus, silicon and germanium are semiconductors. However, if you take diamond, an allotrope of carbon, it has a band gap of 5.47 electron volt. Thus, you need very high energy to excite an electron from the valence to the conduction band. As a result, diamond is an insulator. The most important part of the band structure is valence band maximum and conduction band minimum. Often, the valence and conduction band edges are approximated by a parabola. Let me explain what do I mean by parabolic approximation. This is the conduction band and EC is the energy at the conduction band minimum. We assume that energy increases quadratically in the conduction band. That is, energy is equals to energy at the conduction band minimum plus as we go away from the conduction band minimum, the energy is increasing quadratically as a function of K. Here, ME star is a number which is greater than 0 and it has dimension of mass. Similarly, in valence band, EV is the energy at valence band maximum. And we assume that energy is decreasing quadratically as we go away from the maximum point. That is, energy is equals to energy at valence band maximum and it decreases quadratically as a function of K as we go away from the maximum point. Here, MH star is greater than 0 and it has a dimension of mass. Since at the bottom of the conduction band we have electron-like charge carriers, Me star is called electron effective mass. On the other hand, since we have hole-like charge carriers at the top of the valence band, Mh star is called the hole effective mass. So I have told you about the parabolic approximation. Let us now revisit the electronic band structure of silicon and germanium. Note that actual band structure is quite complicated. For example, there are two bands at the valence band edge of both silicon and germanium. One of the bands is flatter than the other. Moreover, valence and conduction band also has different curvature. How do we account for all such complications observed in actual band structures of a semiconductor? All the complications in actual band structure are included in the term effective mass. We know that effective mass M star is inversely proportional to the curvature, which implies that a flatter band has lower curvature and higher effective mass. For example, the band shown by the solid line has higher effective mass and the band shown by the dotted line has smaller effective mass. Thus, even if we have two degenerate bands at a K point, we can model by using two different values of effective mass. For example, take the case of two degenerate valence bands as shown here. We can write E equal to EV minus H cross square K square by 2m H1 for one of them and E equal to EV minus H cross square K square divided by 2m H2 star for the other one. We take M H1 to be bigger than M H2. That means the effective mass of one band is higher than the effective mass of the other band. In that case, this is known as heavy hole band, and the other one is known as light hole band. This is the heavy hole band having a higher value of the effective mass, and this one is the light hole band having a smaller value of the effective mass. We already know that effective mass is related to the curvature of the band. As a result, a flatter band has higher effective mass. Let us see how it is manifested in density of states plots. Let us take the conduction band and write the energy dispersion relation. E minus EC, where EC is the conduction band minimum, is equal to h cross square k square divided by 2 me star. Now, n of E is equals to number of electrons per unit volume, which is equal to 1 by 3 pi square 2 me star divided by h bar square whole to the power 3 by 2 E minus EC whole power 3 by 2. This expression is very similar to the case of free electrons. We are just writing E minus EC in place of E in this case. Now, we calculate first derivative of Ne with respect to energy, which is equal to 1 by 2 pi square 2 me star divided by h cross square whole power 3 by 2 E minus EC whole power half, and this is equal to the density of states in the conduction band. Similarly, for the valence band, we can write the energy dispersion as EV minus E, where EV is the valence band maximum, is equal to h cross square k square divided by 2 mh star, and we can write the density of states as dNh by dE equal to 1 by 2 pi square 2 mh star divided by h cross square whole power 3 by 2 EV minus E whole power half. This is equal to density of states for the valence band. Thus, if a band has higher effective mass, it has higher density of states at a given energy than compared to a band having lower effective mass. For example, the band shown by the solid line has higher effective mass, and if we take this energy, then this band has higher density of states than compared to this band which has lower effective mass and a lower value of density of states. We have found an important parameter, effective mass. When an electron is put in a periodic potential, it responds to applied field as if it has a mass of m star. M star can be greater than or less than the free electron mass m. M star can even be negative. This is related to Bragg reflection due to the periodic potential. Momentum of an electron changes due to two things. Number one, momentum transfer from the external field. Number two, momentum transfer from the lattice, which happens due to the Bragg reflection. For example, consider an electron having wave vector near the zone boundary. Although K increases by an amount delta K due to the applied field, Bragg reflection causes overall decrease of the forward momentum. Thus, in this region, m star turns out to be negative. Let us try to understand the effect of m star from a practical point of view in a semiconductor. For that, we need to know about mobility. This is an important parameter in a semiconductor. Mobility is defined as the magnitude of drift velocity per unit electric field, that is mu equal to magnitude of drift velocity divided by electric field. Electrical conductivity is proportional to the mobility, and electrical conductivity is a sum of electron and hole contribution. Sigma equal to Ne times E times mu E plus NH times E times mu H, where Ne and NH are electron and hole concentration, and mu E and mu H are electron and hole mobility. Note that mobility is defined as positive for both electrons and holes, although their drift velocity are opposite. Comparing with drift velocity of free electron given by V equal to Q E tau divided by M. From this equation, we can write mu E is equals to E times tau E divided by M E star, and mu H is equals to E times tau H divided by mH star. Thus, mobility is inversely proportional to the effective mass. So, we can conclude that charge carriers travel faster if effective mass is smaller and vice versa. Let me summarize the most important concepts learned in this lecture. Conduction band minimum, abbreviated as CBM, and valence band maximum, abbreviated as VBM, are the two most important parts of the band structure, as carriers in VBM and CBM take part in electronic transport process. Often the band structure near VBM and CBM are approximated by parabolic approximation. To apply parabolic approximation, we need to know the parameter effective mass, or m star, which is inversely proportional to the curvature of VBM or CBM. We have seen that m star is related to the effect of periodic potential. This is the parabolic approximation near CBM, and this is the expression for density of states of the conduction band. Similarly, this is the parabolic approximation corresponding to the VBM, and this is the expression for density of states of the valence band. Note that density of states is proportional to the effective mass to the power 3 by 2. That is, higher m star implies higher density of states. Just by looking at the band structure, we can say many things qualitatively. For example, narrow flat bands have small curvature. As a result, effective mass is high, which implies high density of states and low mobility. On the other hand, wide dispersive bands have large curvature. As a result, effective mass is low, which implies low density of states and high mobility. Note that we would actually like to have a semiconductor with high density of states, because high density of states ensures high carrier concentration and high mobility.